Hey guys, tonight we drift into the quiet heart of creation itself, the birth of a star. Imagine you're floating in a vast ocean of nothing but mist, not water, but hydrogen and helium gas left over from the Big Bang. The air is not air at all, but a cold emptiness, only a few atoms wide. Yet here, in this silence, gravity begins to hum a song so ancient it has no words. You watch as a cloud, perhaps dozens of light years across, starts to fold in on itself. It's patient, imperceptible, like watching the slow inhale of the cosmos. Gravity gathers what was once scattered, pulling every atom closer. As the gas falls inward, it warms, whispering against the dark. You might imagine this as the universe's version of deep breathing: expansion, collapse, creation, release. Within that collapse, pockets of density form. Each one is a potential star, a luminous seed wrapped in darkness. The hydrogen atoms jostle and bump, faster and faster, until the friction itself glows. Temperatures climb into the millions of degrees. At that point, so brief, compared to the cloud's ancient life, a single fusion ignites. Hydrogen nuclei merge to form helium, releasing bursts of light and heat that fight the inward crush of gravity. It's the first flicker of a newborn star. You probably wouldn't survive being shrunk down to atom size to watch this close-up, but we'll try anyway. Picture yourself in the middle of that glowing core, where the temperature soars to 10 million Kelvin, and the density is enough to crush you into nothing. Yet, from this violent pressure, balance emerges. The baby star stabilizes, halting its collapse, glowing softly against the cosmic night. It's like watching a heartbeat begin in a dark womb. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tell me in the comments where you're listening from and what time it is where you are. Now, dim the lights, and let's ease into tonight's journey together. You drift closer to the young star, still cocooned in swirling dust and gas. It's a protostar now, bright in the infrared, hidden from optical sight by the cloud that birthed it. Around it, a flattened disk begins to spin. Inside that disk, grains of ice and silicate bump and merge, forming pebbles, rocks, worlds to be. You're watching not just a star being born, but the blueprint of a solar system unfolding around it. The physics of this process, studied deeply by McKee and Oestreicher, 2007, reveals that turbulence, magnetic fields, and gravity all collaborate in this act of creation. The balance is delicate, too little gravity, and the cloud never collapses, too much, and it fractures into clusters. In this interplay, nature finds a way to sculpt light itself. If you could hear this moment, it would be a slow, deep vibration, like the sound of breath through a flute the size of a galaxy. The young star flickers as infalling gas crashes onto its surface, each impact releasing heat and X-rays into the void. Slowly, its surroundings clear, revealing a glowing orb where once there was only shadow. You float through the remnants of the nebula, the colors faint but mesmerizing. Threads of pink hydrogen emission, blue ionized oxygen, golden dust lit by reflected starlight. It's a cradle and a graveyard in one, where elements from long-dead stars have gathered to give rise to new ones. And maybe, as you watch this glowing infant breathe its first light, you realize something beautiful. Stars are the universe's way of turning gravity into art. Out of cold, empty space comes warmth and brilliance. Out of chaos, pattern. Out of silence, song. Somewhere, in a cloud like this one, our own sun was once forming 5 billion years ago, in the quiet outskirts of a spiral galaxy. It, too, began with that same cosmic sigh, and from its disk, our Earth eventually emerged, carrying the memory of that first ignition in every sunrise. The story of a star's birth isn't just about fusion or gas or physics, it's about transformation. Hydrogen becomes helium, energy becomes light, and the invisible becomes visible. You can almost feel the warmth of that first photon brushing your face, traveling light years through the dark to meet your gaze. Maybe the universe just loves to repeat patterns. The way a cell divides, the way a heart beats, the way a cloud collapses into brilliance. Each one a reminder that even in the coldest emptiness, there is always the possibility of life, of warmth, of beginning again. The star brightens, steadies, and shines. You drift back slowly, watching it take its place among the others, one more flame in the infinite dark. Around it, the nebula still glows softly, a memory of what came before. And in that glow, the next generation of stars is already forming. From dust to fire, from silence to light, this is how every story in the universe begins. You drift closer to the young star, now glowing fiercely in the darkness. Its once turbulent birth cloud has mostly cleared, leaving a radiant sphere of gas suspended in black infinity. Inside, a quiet miracle holds everything together. A fragile, perfect balance between two invisible giants, gravity and pressure. One pulls inward, the other pushes out, and for now, they agree to coexist. You hover above its surface, a glowing ocean of plasma. The light trembles slightly, as though the star were breathing. Every second, deep within its core, billions of tons of hydrogen fuse into helium, releasing energy in the form of light and heat. That energy rushes outward, colliding with particles, scattering, radiating until, after hundreds of thousands of years, it finally escapes the surface as the light you might one day see twinkling in your night sky. This is the star's adolescence, its long and steady youth, a time of equilibrium that astronomers call hydrostatic balance. Inward gravitational pressure tries to crush the star, but the outward push of radiation and thermal energy resists perfectly. Prialnik, 2009. It's like watching a dancer spin endlessly, poised between falling and flying. Inside, the core is unimaginably dense and hot, 15 million degrees Kelvin, where protons move fast enough to tunnel through their mutual repulsion and fuse. Each fusion event releases energy through Einstein's equation, E equals mc squared, transforming a tiny fraction of mass into radiant power. That power holds the star aloft. Without it, gravity would win, and the star would implode. If you listen carefully, you can almost hear this silent tension hum just below thought, the sound of atoms being crushed and reborn. You can feel the serenity of this balance, though it's built upon violence, a perpetual war fought in perfect stillness. As you drift inward through layers of gas, the colors change from golden white at the surface to deep sapphire near the convective zones, where heat rises and falls in swirling columns. These turbulent motions carry energy upward, just as hot air rises from your morning tea. The rhythm of these flows sets the tone for the star's surface brightness, the subtle flickering we call stellar granulation. Each granule, from your perspective, is the size of a continent, shimmering, blooming, fading within minutes. To the naked eye, it looks steady, but up close, the surface writhes like a living thing. You sense the gravity beneath your feet if you had feet. It's immense. On a star like our Sun, you would weigh nearly 30 times more than on Earth. Yet somehow, the outward flow of light keeps it from collapsing into itself. This serene tension will last for billions of years. And maybe you realize, this is the secret heartbeat of the cosmos. Every stable star you've ever seen, every gentle sunrise, every soft twilight glow is a story of balance, of forces that never quite destroy each other, but instead sustain life through their eternal argument. There's a quiet lesson in this. Equilibrium is not peace, but persistence. The star doesn't rest. It burns, constantly, to maintain the illusion of calm. The light, emerging from the surface, now races through space at 300,000 kilometers per second. Some of it will reach a nearby protoplanetary disk, warming dust into clay, awakening chemistry that will one day call itself life. The rest will wander through the dark, shining on worlds we'll never know. If you could touch that light, it would feel like warmth distilled from time itself, a photon born in the heart of fire, now brushing gently against the skin of the universe. Scientists studying stellar interiors use complex models of nuclear fusion, energy transport, and convection to understand this delicate choreography. Prialnik, 2009. But here, floating so close, it feels simpler. Gravity wants to pull everything inward, and light keeps insisting on escape. You think of your own breath, the way your lungs expand and contract. A personal balance between taking in and letting go. The star does the same, only slower, grander. It breathes in gravity, exhales light. Maybe the universe just loves to mirror itself, a star's equilibrium echoing a human's calm heartbeat. Each one fragile, each one fleeting, each one burning quietly against the dark. As you drift farther away, the star looks peaceful again, a single glowing pearl among countless others. You know now that behind that stillness lies a constant struggle, invisible yet magnificent. It is this struggle that keeps the cosmos shining, that turns hydrogen into warmth and warmth into the possibility of life. For now, the balance holds, but it won't last forever. One day, the fuel will thin, the equilibrium will falter, and gravity will begin to win once more. But that's a story for another night, or perhaps the next part of this journey. You hover before a field of stars, each glowing with a different hue: crimson, amber, ivory, sapphire. They twinkle softly in the distance, but now you know they are not simply lights in the sky. Each color tells a story of temperature, age, and energy. The color of a star is its confession, the language of its fire. You drift toward a blue-white star first. It dazzles like an electric flame, almost painful to behold. The heat here is immense, tens of thousands of degrees at its surface, searing hydrogen and helium into brilliance. Its light pierces the dark like a blade. You sense its urgency. Such stars live fast, burning their fuel in mere millions of years before collapsing into spectacular deaths. They are cosmic sprinters, brilliant and brief. Then, you turn toward a red star, dimmer, softer, more patient. Its surface is cool by comparison, only a few thousand degrees. You could almost imagine warmth rather than fire. Its light diffused and gentle, like the glow of an ember beneath ashes. Red stars, called M-dwarfs, live for trillions of years. Their pace measured in cosmic heartbeats slower than time itself. Gray, 2005. Between the two extremes lie the yellows and white stars like our Sunday. Balanced in hue, steady in energy, they form the middle ground of stellar life. The sun's light, golden and constant, is the soft compromise between fury and restraint. Color, temperature, and spectrum, these three are inseparable. Every photon that leaves a star's surface carries a fingerprint, a precise wavelength determined by the energy transitions of the atoms inside it. When scientists spread that light through a prism or spectrograph, they see a rainbow interrupted by dark lines, the Fraunhofer lines, each corresponding to an element, each a whisper from within the star's heart. Gray, 2005. You imagine the universe as a painter's studio. The palette is hydrogen, helium, carbon, oxygen, iron. The brush is temperature. The canvas is time. Every hue we see in the night sky is painted by the physics of heat, by how atoms jiggle and collide, how energy escapes into the void. If you were to translate the light into sound, blue stars would sing in higher pitches, sharp and bright. Red stars would hum in low, deep tones. Together, they form a symphony too vast for human ears, a chromatic harmony played across galaxies. You drift among them, each star radiating a tone of color that mingles with its neighbors. The cluster glows like a slow heartbeat of the cosmos. You realize that color, too, is an act of balance between energy and release, chaos and order. The relationship between temperature and color follows a simple law, the black-body radiation curve, discovered through centuries of physics. As temperature rises, light shifts toward shorter wavelengths from red to white to blue. It's the same principle behind the orange coil of a stove or the white arc of lightning. What you're seeing is not just color, it's temperature made visible, heat translated into light. Gray, 2005. You turn your gaze toward one star in particular, an old red giant nearing the end of its life. Its glow flickers unevenly, betraying turmoil within. In that redness lies exhaustion, not warmth, a sign that hydrogen fuel is fading, fusion slowing. Yet, in its soft hue, there's a kind of peace. The same physics that makes it dimmer also makes it gentler, as though the universe, even in its violence, prefers to fade gracefully. Color also tells us distance. As light travels across expanding space, its wavelength stretches redshifted, lengthened, softened. The farther a galaxy, the redder its light becomes. This cosmic stretching, discovered by Edwin Hubble, tells us that the universe is still expanding, that light itself is pulled by the stretching of space-time. Hubble, 1929. Even photons age, in their own quiet way. You think, perhaps, that the stars resemble people more than we realize. Some burn fast and bright, leaving echoes long after they fade. Others live slow, dim lives, persistent and steady. Some change color over time, cooling, evolving. All are governed by the same rule: energy spent is life lived. You look down at your own hands or imagine them bathed in faint starlight. That golden tone on your skin at sunset, that silver moonlight on water, all of it comes from the same physics. The color of heat, the whisper of atoms, and maybe, just maybe, the universe chose color as its way of feeling emotion. Blue for youth and brilliance, red for age and reflection, gold for balance and grace. The night sky, then, is not cold or empty, it's an ocean of moods, each one glowing across billions of years. You drift backward now, and the colors blend the hot and the cool, the brief and the eternal, until they merge into one soft white radiance. It's the same white that shines from your morning star, the same that gleams in the Milky Way's heart. You realize that every time you look up at the sky, you are seeing time itself in color. Every hue is a record of energy long spent, a diary of the universe's flame. Maybe the stars aren't so far away, after all. They speak in the same language of warmth and fading light that we do born in fire, cooling towards silence, painting the night with the shades of their story. You drift beside a calm, middle-aged star, its fury softened, its rhythm steady. The violence of birth has faded. The fierce blue flames of youth have mellowed into a golden glow that warms the empty dark. For billions of years, this star has done one thing with unwavering grace. It has burned, not burned like a fire devouring wood, but through fusion, the merging of atoms under immense pressure. Deep within, hydrogen nuclei protons collide, overcome their natural repulsion, and fuse to form helium. Each fusion releases energy, a tiny loss of mass transformed into light, an ongoing miracle repeated 10 to the power of 38 times every second. It is a process both ceaseless and patient, one that defines the main sequence. The long, quiet middle chapter of a star's life. Hansen, Kawala, and Trimble, 2004. You imagine drifting down through the surface, past the boiling granules of plasma that rise and fall like continents of flame. Beneath them lies the radiative zone, a vast sea where energy travels not by motion, but by the slow diffusion of light. Photons bounce and scatter, absorbed and re-emitted millions of times. It can take them hundreds of thousands of years to travel from the core to the surface, an odyssey of light through density and time. Deeper still, you enter the heart. Here, in the core, conditions are nearly incomprehensible. 15 million Kelvin, 200 billion times Earth's atmospheric pressure. Protons slam together at velocities beyond intuition. The proton-proton chain dominates in stars like our Sun. For every 4 hydrogens fused, 1 helium nucleus emerges, and a burst of energy escapes. You can almost hear the subtle whisper of fusion, soft pops of creation echoing across the eons. The helium ash drifts slowly toward the center, accumulating as fusion continues outward. Over time, this core will grow denser, but for now, equilibrium remains. It's a perfect feedback loop. When the fusion rate increases, the star expands slightly, cooling the core and slowing the reaction. When the rate drops, the core contracts and reheats, reigniting stability. A cosmic thermostat, infinitely patient. You drift upward again, through layers of transparency and turbulence, until you breach the surface. The light here is golden white, filtered through gases of hydrogen and metals that give it tone and texture. You could almost reach out and scoop a handful of radiance, warm, weightless, alive. And yet, the calm of this long-burning phase is deceptive. Every second, the star converts 4 million tons of matter into energy. It does so without complaint, without change, across eons so vast that human civilizations rise and fall within the blink of its lifetime. This serenity is built on relentless motion, the kind of stability that exists only through perfect imbalance. As you drift farther away, the scale becomes humbling. The star's surface seethes with convection, plumes of gas rising and falling in slow rolling waves. Each wave might take a month to crest. The corona above it shimmers with magnetic loops, flares, and solar wind-charged particles streaming outward to shape planets and auroras across light-years of space. This, too, is the long, quiet, burning the calm facade of continuous creation. Everything it touches changes. Ice becomes vapor, rock becomes molten, chemistry becomes life. Without such long-lived steadiness, there would be no time for evolution, no patient warmth to cradle complexity. Scientists describe this as the main sequence lifetime, a span determined by the star's mass and fuel supply. Hansen et al., 2004. For a sun-like star, it lasts around 10 billion years. a cosmic adulthood where little seems to happen, but everything important does. It's the breathing space between chaos and collapse, between beginning and ending. You float in silence and imagine the photons still journeying outward, long after the ones that reach you now were first born in the core. The light touching your face tonight may have started its voyage when early humans first looked up in wonder. Each ray, a messenger from deep time, carries the signature of a process that never pauses, never hurries. Perhaps you feel a quiet kinship with that light. You, too, are made of slow, invisible transformations. The calcium in your bones, the oxygen in your breath, all forged by stars that once burned like this. They, too, had their long middle lives before their endings turned them into dust and memory. Maybe the universe treasures these quiet spans between extremes. After the chaos of birth and before the storm of death, there is always this, an interval of balance, of simple endurance, the long, quiet burning, where energy and time fold together into something luminous. You linger, watching the surface flicker softly. The star doesn't know it's beautiful. It just is doing what it must, as it always has. And you can't help but think, maybe the truest form of peace isn't stillness, but the steady continuation of light. You drift backward from the calm, golden star until it becomes one among countless others. They shimmer like slow-moving embers scattered through the night. But you notice something now that you didn't before. Some shine fiercely and vanish quickly, while others glow dimly for ages beyond imagination. The difference, you realize, lies not in luck, but in mass. The heavier a star, the shorter its life. The lighter, the longer it endures. It's one of the simplest, most elegant rules in the cosmos, and one of its most poetic, Solaris and Cassisi, 2005. Mass determines destiny. You drift toward a massive blue star. Even from far away, its energy is overwhelming. It burns so hot that its outer layers boil with ultraviolet fury. Its core fuses hydrogen into helium at a staggering rate, 10,000 times faster than the sun's. Every second, it transforms more mass into light than our entire planet weighs. But this brilliance is fleeting. The greater the fire, the quicker the fuel runs out. This star will live only a few million years, a brief but blinding spark in cosmic time. Now you glide toward a faint red dwarf, glowing with quiet persistence. Its light is soft and gentle, almost hesitant. Its temperature is low, barely enough to keep hydrogen fusion alive, but that very restraint gives it endurance. These stars can live for trillions of years, longer than the universe has yet existed. None have died of old age. The cosmos simply isn't old enough for that. If the blue giant is a supernova in waiting, the red dwarf is a candle that never flickers. It's humbling, really, how the same physical laws that create all stars also set their limits. The rate of fusion, the balance of gravity, the temperature of the core all scale with mass. In the universe's mathematics, brightness comes at a price. A star twice as massive as the sun might shine 10 times brighter, but its lifetime will shrink to a fraction. Mass gives energy, but steals time. You might think of this as a cosmic version of a human truth. Those who burn the brightest often live the shortest. Energy and duration exist in delicate opposition. Maybe the universe isn't cruel, just balanced. As you drift between these two extremes, you begin to notice how mass also determines fate. The heavy stars will die violently in supernovae that scatter their guts across galaxies. The lighter ones will fade gently, shedding their outer layers into delicate nebulae, leaving white dwarfs behind. The universe loves variety, but every ending is written in the same ink, gravity and fuel. You move closer to the blue giant again, skimming its surface. You can feel its instability, its restless energy. Its light pulses slightly, not because it's dying yet, but because it's burning unevenly. Inside, convection zones churn, radiation bursts, and the balance wavers. The star's own weight threatens to crush it at every moment, and only the ferocity of fusion keeps it alive. You sense that this cannot last. Meanwhile, the red dwarf's world is slower. Its convection mixes hydrogen throughout the entire star, making its fuel supply efficient. It's a master of conservation, using every atom, wasting nothing. One day, trillions of years from now, it will fade to a dull ember, cooling quietly in a universe grown cold. But that day is impossibly distant, hidden beyond the lifespan of galaxies themselves. Back in the middle ground lies our sun, a modest balance of size and longevity. About halfway through its 10 billion-year life, it shines with patient stability. But even now, deep within, it is slowly changing. Hydrogen dwindles, helium builds. The balance tilts, almost imperceptibly. The sun's brightness will gradually increase over the next billion years, too slow for human eyes, but inevitable. Eventually, its heat will transform Earth's oceans into vapor, and life, as we know it, will fade. All because of mass and time, the two rulers of stars. Astrophysicists like Solaris and Cassisi, 2005, model these lifetimes with remarkable precision. By comparing mass, luminosity, and fusion efficiency, they can predict the entire life trajectory of a star. The relationship follows a simple power law. Lifetime is roughly proportional to 1 divided by the cube of mass. Double the mass, and a star's life is cut to 1/8. It's beautiful in its inevitability, and haunting in its fairness. You drift farther, and the sky becomes a tapestry of fates. Blue giants racing toward death, yellow stars cruising through middle age, red dwarfs barely beginning their stories. You realize that the night sky is not timeless, it's a vast, slow-motion clock, each light ticking toward its own ending. Maybe, as you watch them, you sense a whisper of your own mortality reflected there. Stars die, so do worlds, so does everything that burns. Yet somehow, that impermanence feels comforting. The universe doesn't waste, it recycles. The death of one star seeds the birth of another. Nothing is lost, only transformed. You close your eyes, letting the starlight wash over you like warm rain. The cosmos hums quietly around you, patient and eternal, even as each point of light lives its finite span. Maybe the universe is teaching you this: to live brightly, knowing the light won't last forever. You float beside a star that has begun to change. Its steady rhythm, once so sure, is faltering. Deep within, the balance that held for billions of years now trembles. The hydrogen fuel that powered its radiance is nearly gone, and gravity, patient and relentless, starts to reclaim control. Inside the core, fusion slows. With less energy pushing outward, the center begins to collapse under its own weight. The temperature climbs rapidly, hotter and hotter, until a new kind of fusion stirs helium, ignited by the fierce pressure of contraction. The star's outer layers respond in panic. They swell, cool, and redden. What was once a calm yellow sun transforms into a vast crimson orb. You watch as it expands to hundreds of times its original size, devouring nearby planets, reshaping its entire being. This is a red giant, a star's grand metamorphosis, as studied in depth by Herwig, 2005. It's not dying just yet, it's changing form, finding one last equilibrium. You drift close to the surface, though surface is hardly the right word anymore. It's a translucent ocean of gas, so diffuse that you could pass through without resistance. The color glows deep orange-red, like embers in slow motion. Below, convective cells rise and fall in majestic swirls, each larger than Earth itself. The sound, if you could hear through the vacuum, would be a deep, slow rumble, like thunder trapped inside a cathedral. The star is breathing unevenly now, pulsing with new rhythms. In its swollen heart, helium fusion begins. 3 helium nuclei, tiny carbon seeds, merge into one carbon atom in a process known as the triple alpha reaction. It's a dance of improbable precision, where even a slight change in the laws of physics would make it impossible. Without this delicate alignment, there would be no carbon, no life, no you, Herwig, 2005. You watch carbon atoms being born, each one a miracle of temperature and time. Some fuse again to form oxygen. Slowly, layers of new elements build within the core, like the growth rings of a cosmic tree. As the star burns through helium, the outer layers continue to puff outward. Gravity weakens near the surface, allowing material to escape into space in a soft wind. You can see it, a faint shimmer of particles drifting away, glowing gently as they go. The star is shedding itself, atom by atom, in a long and graceful farewell. This is the phase of life where beauty and decay become one. The red giant, swollen and luminous, paints the cosmos in colors of farewell: copper, amber, ruby, and gold. You float in its glow, weightless, as time slows to a patient crawl. If you look carefully, you can see small knots of dust forming in the outflowing gas. These grains will drift through interstellar space, joining the great molecular clouds from which new stars will one day be born. In its dying breath, the giant is already creating its successors. The process is both violent and gentle. The inner layers collapse and heat, while the outer layers cool and drift away. Each contraction, each expansion, sends out waves of light flares that travel across galaxies. It's a heartbeat of dying radiance, a sign that fusion still fights against the inevitable. You drift inside the star's envelope, through slow-moving rivers of plasma. Here, hydrogen still fuses in thin shells around the helium core, fueling expansion from beneath. The star's density decreases as its radius grows, so vast now that if placed in our solar system, its surface would reach beyond Earth's orbit. But despite its immensity, it feels fragile. Its light trembles, its outer layers quiver. It's as though the star itself knows the end is near, yet refuses to fade quietly. Scientists have studied these final acts with reverence. The red giant phase is the most poetic of all stellar stages, a time when death and creation intertwine. Herwig, 2005. In these immense, unstable atmospheres, elements are forged and released that will someday form rocky planets, oceans, and DNA. You float farther back and watch the transformation unfold in full. What was once a serene yellow sun now fills your view, glowing red and vast, a sphere so enormous it humbles imagination. Solar winds blow outward in waves, creating halos of shimmering dust. The space around it ripples with scattered light. Maybe you think of old age the way it changes form, but not essence. The star is still itself, still luminous, still radiant, even as it surrenders what it was. There's grace in that surrender, beauty in letting go. You realize that this too is balance, just a new kind. The star burns not to survive, but to transform, to return its matter to the great cycle of birth and rebirth. And perhaps, floating here, you find comfort in that thought. Nothing truly ends. The light just changes shape. The red giant shimmers before you, its swollen body trembling in the dark. It no longer burns with the calm certainty it once had. Instead, it quivers slow, rhythmic, almost musical. The light brightens, fades, brightens again. The star has entered its pulsing stage, where each beat is both a sigh of exhaustion and a whisper of persistence. You float just above its vast, uneven surface. It looks like a living ocean of fire. Huge cells of plasma rise from below, cool, and sink again in cycles that take months or years. The star's outer layers expand and contract with each pulse, sending waves of soundless motion through the surrounding space. It's the cosmos's slowest drumbeat, a heartbeat stretched across light years. Astronomers call these stellar pulsations oscillations that occur as the star struggles to find a new balance between gravity and pressure. Inside, helium fusion flickers in fits and starts, building instability that ripples outward. Some of these stars, known as mirror variables, can double in brightness over months before dimming again, each cycle marking another contraction and expansion. Wood, 2000. You can almost feel the rhythm through your skin. A long inhale, a patient exhale. Each breath releases part of the star's body into space. You drift closer, through the reddish haze of its atmosphere. The pressure here is so faint you could fly through it unharmed, yet the light is thick, syrupy, golden red. The brightness swells and falls, the star's own breath patterning the dust forming around it. Within the star, helium nuclei fuse into carbon and oxygen, releasing bursts of energy. But fusion now happens in shells rather than a central core like layers of a burning onion. These shells ignite intermittently, causing thermal pulses that make the entire star throb. Each pulse pushes out a gas farther away, feeding the stellar wind that carries the star's ashes into the dark. You watch a wave roll outward from deep inside. It moves slowly, almost lazily, until it reaches the surface and erupts as a shimmering veil of gas. A new layer of the star's skin peels off and drifts outward. The process repeats, each oscillation carving a new ring in the halo surrounding it. These rings will one day glow as a planetary nebula, an echo frozen in light. There's a strange peace in this repetition. The star is dying, but it's also making art shells of gas that ripple outward like the folds of a flower. If you could see it from far away, it would look like a softly breathing lantern in the void, glowing, dimming, glowing again. Astronomers once thought such flickering was chaos, but it isn't. It's rhythm. predictable, elegant, meaningful. The period of each pulse, measured precisely by instruments, tells scientists the star's mass, size, and internal structure. Wood, 2000. The universe has its own metronome, hidden in the throats of dying suns. You drift back and watch the flickering in slow motion. The star brightens white light blooming briefly from its center, then cools again to crimson. It's as if it's struggling to speak, to tell you something about endings. Maybe that's all light ever does. Try to say what cannot be said with silence. The expanding waves of gas collide with older shells, forming filaments that glow faintly. You realize that what you're witnessing is memory made visible, each pulse recording a moment of the star's history, frozen in space. Even after the core collapses, these ripples will remain for thousands of years, drifting farther into the void, carrying traces of the elements it forged. Inside one of those waves, new dust grains form carbon and silicate crystals that glint like snowflakes. You reach out, and a few pass through your hand, silent and weightless. Someday, grains like these will be part of a new solar system. Maybe they'll fall onto a planet, dissolve in rain, and sleep beneath alien soil until life awakens them. The heartbeat of this dying star will live again in new hearts. You look back at the giant. It pulses once more, brightening, then dimming, its glow settling into calm. You sense it's nearing its last few breaths. The outer layers are growing thinner. The light that escapes now carries away the final fragments of its body. There's a tenderness to its decline. The star is not failing, it's giving. Each pulse is a gift. Each wave of light a promise that nothing truly disappears. The atoms it releases will become clouds, and the clouds will one day become light again. Maybe that's how the universe says goodbye, through repetition, through rhythm, through the quiet music of expansion and release. The pulses fade. The crimson surface of the giant softens, its flickers now slower, heavier, like the last beats of a weary heart. You drift closer, through layers of thinning plasma, into the furnace beneath. Here, deep inside, something profound is happening, something that will soon end everything. For billions of years, the star has survived by fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon and oxygen. Each step released energy that pushed outward, balancing gravity's pull. But now, deep in the shrinking core, that sequence approaches its end. Iron begins to form. It's an astonishing moment, not because it brings creation, but because it stops it. Iron marks a boundary, a cosmic stop sign painted in starlight. Up to this point, fusion created energy, but fusing iron, instead of releasing energy, consumes it. The math of nuclear physics, unbending and absolute, allows no exceptions. Beyond iron, a star can no longer generate power to resist collapse. Arnett, 1996. You float near the edge of the core, where temperatures reach 100 billion degrees, yet there is stillness. The once lively churn of fusion ceases. Photons, neutrinos, and atomic fragments flicker briefly, then vanish into silence. The core, now composed mostly of iron and nickel, grows heavier and denser, pressing inward under its own immense gravity. The outer layers, still alive with residual burning, do not yet know the truth. They continue their quiet dance, unaware that the heart beneath them has already gone still. You imagine standing there, feeling the weight of inevitability, the sense that even light cannot escape the arithmetic of entropy. Inside this fading furnace, electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos. The pressure rises faster than the star can respond. The balance that defined its entire life shatters in an instant. This is the moment before collapse, the fragile silence between existence and implosion. If you could see inside a single atom, you would witness matter itself, rebelling against compression. But gravity is merciless. It does not argue. It pulls, it compacts, it demands everything back. Iron's formation, though it marks the star's death, is also a turning point for the universe. All the elements that make up you, carbon in your muscles, oxygen in your lungs, calcium in your bones, were possible because generations of stars reached this same fatal threshold. They built up to iron, and in dying, transcended it. The physics is unforgiving, but there's something profoundly human in it. The idea that creation always comes with limits. Every flame, no matter how bright, consumes the fuel it depends on. You drift in silence. Around you, the atmosphere of the giant grows unsteady, rippling with strange energies. The core contracts faster now, shrinking to the size of Earth in seconds. Its density surpasses anything you can imagine. 1 billion tons per cubic centimeter. The star's identity unravels. The once stable layers begin to fall inward, accelerating toward the collapsing center. The infalling matter slams into the core and rebounds outward, creating shockwaves. The star's surface trembles, unaware that deep within, something extraordinary and final is about to ignite. The universe has built a perfect paradox here, death as the precursor to creation. Without this collapse, there would be no supernova, no gold, no life. You are watching the universe prepare its grandest alchemy. You can feel the tension now, a deep vibration coursing through space itself. The star is poised on the edge of catastrophe, its balance irreversibly broken. The moment of collapse is coming, the instant when gravity wins and light loses. And yet, even here, amid the rising doom, there's beauty. The iron glows faintly, like a cooling ember refusing to die. The laws of physics are about to rewrite matter itself, but the star's glow remains gentle, almost serene. You sense that what's coming will be fast, too fast for even thought to follow. But before it happens, there's a breath, a pause, a perfect stillness. The star seems to know that this is the end of what it was, and the beginning of what it will give back. Maybe that's what the universe has always done, build towards stillness, only to transform it into light once again. And then it happens. The stillness breaks like glass. The iron core, no longer able to bear its own weight, collapses in less than a second. The atoms themselves implode. Electrons and protons squeeze together until there is nothing left but neutrons, dense, indivisible, stripped of identity. You can almost hear the silent scream of matter itself, folding in upon its own existence. In that instant, the core shrinks from the size of a planet to the size of a city. The collapse is so sudden that the infalling outer layers crash into it at a quarter of the speed of light. A shockwave ripples outward, but it stalls, choked by the immense weight of the star's body falling in. For a heartbeat of time, everything hangs in limbo. Gravity devouring everything, light trapped in confusion. And then, neutrinos. Trillions upon trillions burst outward in a furious storm, carrying away energy equal to the light of all the stars in the observable universe. Though for barely 10 seconds, Betha and Wilson, 1985. They pour through you as you float there, ghostly particles that almost never touch anything. Yet here, they are the silent heroes, transferring the pressure needed to revive the dying shockwave. The wave reignites, the core rebounds, the collapse reverses with catastrophic force. You are watching a supernova begin. The shockwave rips outward, tearing through the layers of carbon, oxygen, and silicon. Temperatures soar to billions of degrees. Nuclei collide in chaos, forging new elements in flashes of brilliance. Iron shatters. Nickel, cobalt, and gold are born. The star that has lived in patient equilibrium for eons ends itself in less than a moment of human thought. If you could see this from afar, the light would be so bright it could outshine an entire galaxy. For weeks, it would dominate the sky, a beacon of death and rebirth visible across millions of light years. For a moment, the universe itself seems to blink. You drift within the explosion, but somehow the violence feels graceful. The outer layers are flung away at thousands of kilometers per second, yet the geometry is symmetrical, beautiful rings and tendrils expanding like petals of a cosmic rose. The gases glow in ultraviolet and X-ray, painting the dark with brief, radiant color. You remember the star's slow heartbeat from before? Its gentle pulses. This is the final pulse, the one that releases everything. The shockwave plows through the dying star's body, scattering atoms that have been fused over billions of years. The heavier elements sink outward in layers, carbon and oxygen, then silicon, then iron and nickel. Each fragment carries a story, each will drift into space, someday becoming part of a world, a creature, a thought. At the center, what remains of the core compresses even further. Neutrons lock together in perfect density. A teaspoon of this matter would weigh 1 billion tons. If the core is small enough, it will stabilize as a neutron star, an object so dense and hot it glows faintly in X-rays. If not, if gravity still wins, it will continue collapsing, past the reach of physics, into a black hole. But that comes later. For now, there is only the explosion, the star's final act of generosity. The shockwave expands outward, shredding the interstellar medium, sweeping up dust and gas, mixing it with new elements. You see filaments forming, curling into shapes like smoke. These will linger for millennia, the ghost of a star, shimmering in the dark. The energy of the explosion is almost beyond comprehension. In a single second, the supernova releases more energy than the sun will in its entire lifetime. And yet, amid this destruction, the universe builds its future. Every atom heavier than iron, gold, silver, iodine, uranium is forged here in this single breath of annihilation. You float among the fragments, each glowing ember a promise of creation. The heat subsides. The brightness begins to fade. You look back at the expanding cloud and realize it is both grave and womb, a funeral pyre that seeds the next generation of light. Maybe you think of endings in your own life the way they feel absolute, irreversible. Yet here, in the death of a star, you see the opposite, that every end is simply the start of rearrangement. The atoms released here will drift, collide, cool, condense. They will one day form another star, another planet, perhaps another being who will look up and wonder. You turn once more to the empty space where the star once burned. The core is gone, but its light, its final message, still travels outward, across centuries and galaxies. Long after everything else fades, that light will keep moving, unstoppable. Maybe that's the universe's quiet truth. Even when the heart collapses, the light still finds its way out. You float in the silent aftermath. The once brilliant supernova has dimmed to a soft glow, a slowly expanding cloud of ash and color. The violence has passed, but in its wake lies something miraculous. Inside this chaos, new matter is being forged. Elements heavier than iron, born in the crucible of destruction. You are witnessing the universe's greatest act of creation, nucleosynthesis, the birth of gold, silver, platinum, and uranium. Cowan and Thielemann, 2004. Each speck of light around you is a newborn atom, stitched together in the heat of collapse. Neutrons released in torrents from the imploding core slam into iron nuclei faster than they can decay. This process, known as the rapid neutron capture, or R process, transforms simple atoms into complex ones, building entire families of heavy elements in less than a heartbeat. You can almost feel it happening, the thrum of energy, the dense fog of particles colliding and merging. In the span of seconds, the periodic table grows richer. From the chaos emerges beauty. Gold glints within the glowing dust. Silver crystals shimmer faintly in the cooling air, and radioactive isotopes pulse softly like embers in the dark. For a brief, incomprehensible moment, this cloud contains everything that will ever make up the worlds to come. The light shifts from blue to amber as the gases expand and cool. You drift through the layers, hydrogen and helium on the edges, carbon and oxygen in filaments, heavier metals buried deeper. The smell of ozone would fill your lungs if you had any. The taste of iron would sit on your tongue. Here, chemistry and poetry merge. The raw process occurs only in extremes in the heart of supernovae or the collisions of neutron stars. It's a rare, furious mechanism that builds the elements that make life sparkle and civilizations thrive. Every atom of gold in your jewelry, every trace of iodine in your blood, every spark in a reactor core, each was forged in a dying star like this one. Cowan and Thielemann, 2004. You reach out to touch the drifting debris, and your hand passes through a trail of shining dust. Each particle is an origin story, a future continent, a ring, a heartbeat. The same gold that will one day rest on a human finger now glows here, newborn, still hot from creation. Around you, the debris cloud grows vast. Within years, it will expand across trillions of kilometers. Within millennia, it will fade into the interstellar medium, a diffuse mist invisible to the naked eye. But the elements it carries will survive, wandering through space until gravity gathers them once again. You can almost see the next chapter beginning. These atoms will drift into a molecular cloud, cool and clump. In another few billion years, they will form a new star, perhaps with planets of rock and ocean. Somewhere, a living being will dig that gold from the ground, unaware that it was born in a cataclysm beyond imagination. In that sense, This explosion isn't destruction, it's inheritance. The universe is cyclical in its generosity. Death feeds birth, decay breeds structure. What feels like an ending is really a dispersal of possibility. In a supernova, you can trace the entire arc of creation, from hydrogen's simplicity to the complexity of life's elements. As the light fades, you drift near the cooling remnants of the core, a glowing ember, now stable. Around it, magnetic fields twist the charged particles into arcs of light, weaving through the dust like silk threads. You realize that even the patterns of these magnetic lines will seed structure in the next generation of stars. The explosion's echo reverberates through space waves of energy that will travel for millions of years. One day, they'll reach distant worlds as cosmic rays, altering atmospheres, sparking mutations, perhaps igniting new forms of life. The reach of this one event extends farther than any life form could imagine. And maybe, as you watch it, you feel an odd tenderness toward it all. This chaos, this unbearable beauty, it's the same energy that will one day shape the mountains, oceans, and hearts of creatures not yet born. You close your eyes, letting the golden dust settle around you. You feel time stretch, the violence quieting into calm. The glow dims from gold to red, from red to black. The forge has gone cold, but its creations have only just begun their journey. Maybe that's the secret of stars. They die not to vanish, but to multiply, to scatter themselves into everything that will ever exist. You drift through the golden ashes of the exploded star, now spread across light years. The chaos has slowed into silence. The brilliance has softened into a thin, glowing mist that stretches and curls like the breath of some sleeping giant. You are floating through what was once a single being of light, now reborn as stardust. This dust moves gently, guided by faint magnetic whispers and ancient momentum. Shockwaves still ripple outward from the explosion, carving ripples in the interstellar medium. The star's remains now mix with surrounding clouds of gas, turning the black of space into a faint watercolor wash of color. In infrared, it glows like a living nebula. In visible light, it shimmers faintly, a veil of silver and bronze. Each particle here carries the memory of its origin. One grain of carbon might travel for millions of years before joining another. One atom of calcium might eventually form part of a rock, a shell, or a bone. The universe has no waste. Every speck of matter finds purpose again. Dielet Ali, 2006. You reach out, and the dust passes through your hand like smoke. If you could look closer down to the atomic scale, you would see lattices of carbon forming the first structures of graphite, tiny crystals that reflect the faint light of distant suns. The first hints of chemistry begin to take shape here, in the darkness between stars. The supernova's shockwave continues to expand, ploughing through the interstellar medium, collecting material as it moves. Over tens of thousands of years, it becomes a vast shell, a glowing remnant tens of light years wide. The gases inside cool and radiate energy in X-rays and radio waves. Astronomers on far-off worlds will someday detect this signal and know that a star once died here. You can almost see them, future observers, peering through telescopes, tracing the delicate filaments of gas that once burned with unimaginable heat. They will give it a name, catalogue it, and study its light. But you, here now, feel it directly. The slow dispersal of memory into the quiet fabric of space. The nebula drifts and expands. Pockets of gas cool enough to condense begin to clump together. In those dense knots, gravity starts its slow work again, tugging, compressing, preparing the next generation of stars. Each collapse, each ignition, each birth will carry atoms forged in this very explosion. It's strange to think that something so violent could lead to such serenity. The filaments that curl and stretch look almost delicate, like spider silk. You trace them with your gaze: crimson oxygen, blue hydrogen, green iron, each wavelength of light a clue to what remains. It's like reading a poem written in spectral lines. As you drift farther, you sense how interconnected it all is. The ashes of this one star will not remain in isolation. They will blend with the remnants of others, mixing endlessly until there is no telling where one story ends and another begins. Perhaps one particle of gold will someday be part of a comet, then part of an ocean, then part of a living cell that wonders where it came from. In that wondering, the universe will remember itself. Scientists who study the diffuse glow of radioactive isotopes, such as aluminum-26, have found their signals scattered across the Milky Way, direct evidence of such recycling, DL et al. 2006. Every glowing trace is a breadcrumb, marking the trail from star death to planetary birth. You float on through the cooling cloud. The light grows dimmer. The shockwaves stretch thinner, losing their form. Yet even now, the nebula is not gone. It has simply become part of everything else. You realize that ashes to everywhere is not just a phrase, it's a physical truth. Matter, in the end, is a traveler. It never rests. It just changes form, forever. And maybe, as you watch these drifting atoms fade into the void, you feel a sense of belonging. Because somewhere inside you, in the calcium of your bones, in the iron of your blood, this story is already written. You too are one of the ashes scattered long ago. The universe breathes out, and you breathe with it. You drift closer to the center of the explosion's remains, where something still gleams with strange, condensed light. Amid the fog of drifting gas, a small, impossibly dense object spins rapidly, a remnant of the star's once mighty heart. It no longer shines like a star, yet its presence bends the very space around it. This is what survives the supernova's fury. A neutron star, or perhaps, if gravity was too strong, a black hole. Shapiro and Tucholsky, 1983. You approach slowly. The light distorts. If it is a neutron star, its radius is no more than 20 kilometers the size of a small city, but it contains more mass than our Sunday. You hover above a surface that isn't solid in any earthly sense. A crust of neutrons locked together so tightly that a teaspoon of it would weigh 1 billion tons. The magnetic field hums through you, 10 trillion times stronger than Earth's, enough to bend atoms into threads. It spins fast hundreds of times per second, releasing beams of radiation that sweep across the cosmos like lighthouse beams. Each rotation sends a pulse of energy outward, so precise that distant astronomers will use it as a cosmic clock. They will call such stars pulsars, unaware of the silence that surrounds you now. The pulse isn't sound. It's light, shaped by rotation, time made visible. As you drift closer, you can feel space itself bending, the way heat distorts air above a flame. Gravity here doesn't just pull, it curves. Light, trapped by the star's intensity, skims and swirls before escaping. Time itself slows. You realize that here, near the edge of this collapsed heart, seconds stretch into eternity. If the core had been slightly more massive, just a few solar masses heavier, this remnant would not have stopped at neutron density. It would have continued collapsing, past the point where matter can resist, into a black hole. You gaze into the dark nearby and see one forming. An event horizon, silent and absolute. The black hole's edge isn't a surface, but a boundary, where light can orbit endlessly before falling inward. Space folds into itself. You can feel the curvature, a kind of gravitational vertigo. The photons that try to escape twist around the hole in spirals, forming a glowing ring called the accretion disk. Gas falling inward heats to millions of degrees, emitting X-rays that scream across the void. You understand now. This is not death, but transformation taken to its final extreme. The neutron star is matter made dense. The black hole is matter made absence. Both are endpoints and beginnings. Scientists such as Shapiro and Tucholsky, 1983, describe these objects as the natural consequences of Einstein's equations. What was once theory, the warping of space-time, the trapping of light, becomes reality here. You see general relativity not as math, but as landscape. You drift near the horizon but dare not cross. The black hole's gravity extends far beyond its visible edge, drawing the nearby nebula into long, spiraling arms. Even as it consumes, it shapes. Jets of plasma erupt from its poles, traveling at nearly the speed of light, shooting thousands of light-years into the dark. It feeds, but also gives, stirring the galaxy's gases, seeding turbulence, igniting the birth of new stars in distant clouds. You hover at a safe distance, watching these twin legacies, one remnant spinning in measured pulses, another devouring and reshaping everything around it. Both are monuments to what once was. Both ensure that nothing ends in vain. Maybe you find it comforting, this reminder that even collapse can create motion, that even darkness contributes to the pattern. Time passes differently here. A second might be a century elsewhere, yet to you it feels like a deep, slow breath. The neutron star's pulses continue, steady and eternal. Each one carries the memory of the star that once was, a rhythm echoing through space. You close your eyes and listen, not with ears, but with attention. The pulses merge into a heartbeat, slow, deliberate, endless. It is not the heart of the dead star anymore. It is the heartbeat of the universe itself, steady beneath all its transformations. And perhaps, as you drift between the cold precision of the neutron star and the silent hunger of the black hole, you sense a truth both humbling and beautiful. There is no such thing as stillness here. Even in the universe's deepest quiet, motion remains. Even in loss, gravity composes new forms of grace. The violence is long gone now, yet its echo remains light, still whispering across the universe. You drift through the aftermath, where the supernova's shock has cooled into delicate filaments of color. The wreckage stretches in tendrils thousands of trillions of kilometers long, glowing faintly in the cosmic dark. Each strand is a memory, each shimmer a voice from long ago. This is a supernova remnant, and though the explosion itself lasted only moments, its afterglow will persist for tens of thousands of years. You hover inside that light, a diffuse cathedral of dust and gas, and listen to what it has left behind. The gases ripple and twist, still shaped by the explosion's original momentum. Radio waves hum from within, whispering frequencies that trace the edges of expanding shells. X-rays flicker faintly, revealing where shock fronts still heat gas to millions of degrees. It's chaos, yes, but elegant chaos, a fractal of energy frozen mid-motion, far across the galaxy. Intelligent beings someday will build instruments to study this glow. They'll measure its size, its temperature, its chemical fingerprints. They'll call it a remnant, catalogue it with a number, maybe give it a poetic name. Green, 2019, lists hundreds of them. Each a ghost star identified by its scars, Cassiopeia A, the Crab Nebula, SN 1000, and 6 monuments of light that mark where a heartbeat once echoed. You float through one such shell, brushing past ribbons of oxygen glowing in turquoise, sulfur shimmering deep red, and hydrogen lingering in soft pink waves. The colors pulse faintly, like the last note of a song that refuses to end. If you reach out, you can almost feel their texture silk made of plasma, warm and weightless. Every ripple still moves, expanding slowly through the interstellar medium, reshaping space as it passes. The gases mingle with ancient clouds, stirring the ingredients for the next round of creation. It's a chain reaction that spans eternity, light giving way to dust, dust to gravity, gravity to light again. You pause to gaze outward, and the scale humbles you. The entire nebula stretches over dozens of light years, the width of 100,000 solar systems, yet it began as a single point of collapse. From one imploding heart came a tapestry large enough to outlast civilizations. Time flows differently here. To human eyes, this expansion is invisible. The remnant appears frozen. But if you could return every 1,000 years, you'd see it grow and fade, its edges thinning, its colors dimming. Eventually, in tens of thousands of years, it will disperse completely, its gas merging into the invisible ocean of interstellar space. The memory will dissolve, but its atoms will endure. You wonder if this is what time feels like to the universe, a long exhalation, a slow drift from brilliance to stillness. Scientists once thought of these remnants merely as debris. Now they know them as storytellers. Their light reveals the composition of the star that died, the velocity of the explosion, even the behavior of magnetic fields that shape galaxies. Green's 2019 vast catalogue of supernova remnants reads like a cosmic genealogy, the archives of all who have burned and ended, all who have given their substance to the next. You look again at the tendrils of gas, curling like veins of light. Somewhere in their glow, you realize, is iron, the same kind that carries oxygen through your blood. The same atoms that once pulsed in a stellar core now pulse in living veins. You, too, are a remnant, an echo made flesh. The realization arrives softly. Like dawn, we are the light that remembers. You drift toward the nebula's edge, where the gases fade into black. Beyond lies the endless dark of the galactic void, dotted with other remnants, other stories. You see them faintly, bubbles of light scattered through the night, each one expanding, glowing, whispering across time. And though the star that created this one has been gone for eons, its light is still traveling, still reaching eyes not yet born. Maybe someone, somewhere, will look up at their night sky, point to that faint patch of color, and wonder where it came from. And in that wondering, the star will live again, because the universe remembers itself through curiosity, through every gaze turned upward, through every breath of awe that follows. You drift on, letting the faint radio hum of the remnant pass through you like music. It's fading now, but not gone. Even silence, you realize, has an afterglow. You drift farther, until the glowing tendrils of the remnant fade into the soft dusk of the galactic plain. The echo of the explosion dissolves into silence. Yet even as the light thins, you can feel something gathering invisible, patient, inevitable. The ashes are beginning to fall back together. This is the circle of creation, the quiet return. The dust that was scattered now drifts into new clouds, meeting other remnants, merging into the vast molecular mists that fill the Milky Way's arms. Over millions of years, gravity will begin to pull these particles toward one another, weaving them once again into stars. You move through one of these stellar nurseries, a cold, sprawling nebula, dense enough to birth suns. From afar, it looks like smoke illuminated from within. Up close, it feels alive. Tendrils of carbon monoxide and hydrogen ripple slowly, responding to the faint tremors of passing starlight. You can almost hear it, a sound too deep for human ears, the murmur of gravity at work. Here, the cycle continues as it always has. Atoms once fused in the heart of an ancient giant now collapse into a new seed of light. Inside these regions, where temperatures drop to just a few dozen degrees above absolute zero, molecules stick together, forming the first outlines of future stars and planets. You watch as a small knot of gas begins to condense. It brightens imperceptibly, its density increasing. The dance you've already witnessed collapse, ignition, balance begins anew, quietly and unhurriedly. This is what astrophysicist Francesca Mattucci, 2012, calls the chemical evolution of galaxies, the endless recycling of matter, where every generation of stars enriches the next. The oxygen you breathe, the calcium in your bones, the silicon in your phone, all part of this loop, this slow symphony of death and rebirth. Nothing is wasted, nothing truly ends. You drift closer to the forming star. Around it, a disk begins to spin, the same kind of disk you saw at the start of this journey. But now you recognize the ingredients. Gold from one supernova, iron from another, water vapor, carbon dioxide, ammonia, each a relic of older lives. Within this swirling chaos, planets are already coalescing, rings of dust collapsing into rock. You realize the star we watched die has not vanished. It has become plural. Its body has dispersed across 1,000 light years, seeding countless systems. Its legacy is not a single light, but many. In this way, the universe behaves less like a machine and more like a living organism. It sheds and renews, forgets and remembers, inhales and exhales. The dust of one generation becomes the breath of the next. The light around you softens as new stars begin to form. Their glow filters through the remaining gas, painting the nebula in rose and indigo. The whole region looks like the inside of a sleeping creature's lungs, expanding gently with each breath. You think of the first star, the one that began this journey, that burned so patiently for so long. Its elements have traveled far, but its purpose continues. Even now, in this new cradle, its atoms ignite new fusions, new colors. You can almost sense it smiling, somewhere in the equations of light. Scientists studying this recycling process call it galactic enrichment, but the phrase doesn't quite capture the poetry of it. What happens here isn't just enrichment, it's remembrance. Every star is a memorial to those that came before, each one writing its lineage into the chemistry of space. You close your eyes and feel the rhythm of it. Birth, balance, death, renewal. A circle vast enough to hold galaxies, yet simple enough to echo the beat of your own heart. Maybe that's why we find comfort in looking up. When you gaze at the night sky, you're not just seeing stars, you're seeing the story of everything, how destruction becomes creation, how endings feed beginnings, how the universe keeps itself alive. The cycle continues, quiet and eternal. The dust gathers, the clouds collapse, light is born again, and somewhere, deep in that new light, a world will form, one with oceans, winds, and eyes that will one day look back and ask, where did we come from? You already know the answer. You hover now above a small, quiet world, one orbiting a gentle middle-aged star, somewhere deep in the spiral arms of a galaxy that hums with the breath of 1 trillion suns. The sky above glows with familiar colors: golden sunlight, blue air, white clouds drifting across the curve of oceans. You drift downward, slowly. There's something glinting on the surface, below a thin ring of metal resting on a hand. It catches the light just so, flashing a whisper of yellow warmth, and in that reflection, the whole story you've witnessed unfolds again. That ring, that piece of gold, was born in the dying heart of a star. Long before this world had names, before mountains and wind and oceans, the atoms in that gold lived through a supernova's fire. They were forged in the crucible of collapse, in the furnace of neutron capture, where gravity and energy met in perfect, devastating balance. Burbage et al. 1957. You can almost trace its journey. From the heart of that explosion, hurled across light years, drifting for billions of years through interstellar space, until gravity caught it again, pulling it into a new star system, where it mixed with dust and rock. Over eons, it cooled, sank into molten planets, rose again through volcanic veins, and finally, on this world, it was found, shaped, and worn. The universe has memory. It remembers in elements, not words. You touch the gold. It's cool, solid, unassuming. Yet in its stillness lies a history older than Earth itself, older even than the galaxy it shines within. In that moment, you realize that this quiet metal connects everything: the life and death of stars, the breath of the cosmos, and the small human wish to preserve beauty. Something that began in fire now rests upon a human hand. A promise, a bond, a circle like the one that binds stars to their ashes, and ashes to new light. You look up, and the sky above shimmers with that same truth. Every atom in your body, the oxygen in your lungs, the iron in your blood, the carbon in your skin, was forged in a place like the one you've just traveled through. You are, quite literally, made of starlight. Perhaps that's why, when we gaze at the night sky, something inside us feels like home. The universe is not separate from us. It's within us, in every cell and heartbeat. We are not the observers of its story, we are its continuation. You stand by the sea, feeling the pull of gravity that was once a stellar force. The light of the setting sun scatters across the water, painting gold across the waves, the same gold that was once dust, then plasma, then metal, now memory. You watch it for a while. The wind carries the scent of salt and warmth. The light dims, and you think, maybe that's what stars were always trying to say, that life is how the universe remembers its own brilliance. You take one last look at the ring, its surface gleaming faintly with borrowed starlight. Somewhere, a child looks up at the same sky, tracing constellations that began as the ashes of stars. Somewhere else, a scientist peers through a telescope, catching photons that left their source before humanity existed. It all loops together: creation, reflection, curiosity, wonder. Maybe the universe just loves circles. Maybe that's why gold shines in the shape of one. You close your eyes. The starlight lingers on your skin, and in the silence that follows, you feel it, the pulse of eternity, beating softly through the atoms that were once a star's final breath. The light fades now. The story drifts toward quiet. You float between stars, among the slow-turning arms of galaxies, feeling the hush of everything still at work. Hydrogen still gathers. Gravity still hums. Even when no one watches, the universe continues its patient ritual of creation. The explosion you witnessed has become part of the background, its radiation stretched into microwaves, its dust settled into the gentle arms of nebulae. The cosmos never forgets, but it forgives everything. Every act of collapse is softened by time. Every burst of fire cooled into peace. You breathe in slowly, imagining that each inhale contains a little of that same stardust. And it does. You are living proof that even chaos can become consciousness, that the end of one light can kindle another in the form of thought, memory, and love. The universe is still here, quietly working while you sleep, binding atoms, fusing elements, carrying photons from one side of eternity to the other, all of it humming softly beneath the same laws that shaped you. You are not small. You are precise, a pattern in a pattern, a brief shimmer in a grand design that never ends. So, as you drift into rest, remember, somewhere, another star is beginning to glow. Another story is being written in light. And maybe, one day, those photons will find you again. The stars keep breathing. The circle continues. Sleep now, under their steady, silent watch.